Hi, I'm Henry. I helped acquire the hardware for this project, and I'm the editor for the video. We are NeuroTech at UCSD, and this is our motor imagery controlled app for Google Street View, MiMap. With the onset of COVID, we miss going to campus and exploring the outdoors, but paralyzed patients can't even use Google Maps. Brain-computer interfaces can be very helpful for inputting general commands on a computer and can be used to play Minecraft, explore Google Street View, and control other apps that require a limited set of input commands. We wanted to build a system that would enable a paralyzed patient to input more commands on the computer. Our solution was to provide an all-in-one motor imagery training app that would output key commands given the neural data.
Hello, my name is Simon. I'm the project lead for this project. I worked on the initial research state for the classification models, and I also worked on the calibration GUI. In order to gain useful insights from the EEG signal, we first looked at what happens to the brain during the motor imagery task. Our movements of the arms are closely associated with the primary motor cortex, and multiple rhythms change differently during the actual or imagined motor movements, notably the mu rhythm. When we move our arms or imagine doing it, the mu rhythm, which is around 9 to 11 Hz, decreases its power in the contralateral side. And indeed, after we take the average power spectral density for left versus right-hand trials in the BCI competition dataset, there is a notable power difference in the mu rhythm between these two trial types. There is a significant decrease in alpha power in the C4 electrode for the left-hand trials and decrease in C3 for the right-hand trials. And because of the consistent predictability of such change in response to mental processes for the task, and the fact that it's common across most individuals, it has its own term called event-related synchronization or desynchronization. To ensure the success of this project, I tried to keep our experiment design as close to the original study as possible. Inside each trial of the original study, a fixation cross is first shown at the center of the string, followed by a beep. And 1 second later, either a left or a right arrow is presented to prompt the subject to imagine a motor movement with the corresponding arm. Note that the movement itself can be of the choice of the subject, but they are instructed to imagine the muscle movement rather than the pictorial view of it, and try to refrain from actually moving the arm itself. This should ensure that any insights from the data is actually caused by the motor imagery rather than the muscle movement itself.
Hi, I'm Jiling. I helped with the hardware and helped build the power bin model for this project, and in the end, I was helping with the full system testing. The headset for this project was hacked together by using the Velcro strip from the OpenBCI kit, along with the spiky electrodes to make the device a dry EEG headset. Additional hairbands were used to hold the Velcro strip down and in alignment with the motor cortex. This was important to make sure we get the most signal out of the motor cortex region for distinguishing motor imagery. An ear clip was used for reference and CZ was used for ground.
The software for this app is developed completely using Python. The individual components such as the classification algorithm and the calibration app are tested individually during the development using Jupyter Notebook. Here's a list of the specific packages we use for this app. OpenBCI is used to work with our specific headset. Tkinter is a Python graphics library which we use to program the graphical user interface for our app. sklearn is used to program the classification model, and functions in PyEEG is used to implement the feature extraction critical to this project. Last but not least, NeuroDSP is used for the initial signal filtering. To train the model, we first need to provide a standardized way of formatting the dataset. Our in-house dataset should look very similar to the BCI competition dataset, as we first use that to test our classification models before using the same models on our in-house dataset. Of course, as the finished app records the EEG behind the scenes, it saves the dataset in the same format as well. The dataset consists of two spreadsheets, the EEG data and the event data. The EEG data contains the electrode readings from the 4 electrodes every 4 milliseconds, and the event data logs the trial types, a timestamp at the beginning of each trial. Before training the model, the dataset is first cleaned and bandpassed from 1 to 50 Hz and notch filtered at 60 Hz to eliminate noises. Then using the event data, we extract 4-second chunks of EEG data from each trial and save them onto a data frame, which is then used as the training epochs. In order for the algorithm to classify left versus right-hand trials, useful features need to be extracted from these epochs. But once we obtain those features, the training itself is very simple. The algorithm stacks linear discriminant analysis and logistic regression and choose whichever that gives the better validation score. Once the training is complete, the model is saved onto a pickle file for user feedback as well as the actual map navigation function. Only 20 trials is sufficient for the training of the model, and all of these training can be completed in less than 3 seconds.
EEG pre-processing is an important step for this project because otherwise we would get data that looks like the red blob in the upper right corner of the slide. After filtering between 1 and 50 Hz and notch filtering at 60 Hz, we have something that looks much more reasonable for EEG. Taking the log of the power spectral density, we can see that there is a minor drop-off in the power for higher frequencies, which is what we expect to see for EEG data. The power spectral densities, or PSDs, for the recorded data were further analyzed for each event type. Here you can see the PSDs from 15 trials of each class averaged for each channel to see how the average power values vary between the two classes. We can see how the left-hand motor imagery case, the contralateral electrodes C2 and C4 exhibited smaller powers in the alpha range. The effect for the right-hand motor imagery case was less apparent visually, but could be potentially explained by the narrow alpha peaks in C1 and C3 electrodes. This is a power bin analysis of two electrodes, C1 and C2. These graphs allow us to more clearly see the differences in the classes when we want to use them in our model. We can see here that the alpha range for C1 and C2 may not actually be the best differentiators of the two classes due to the large standard error of means. Rather, as we will see later, the C2 delta range was one of the more prominent differentiators of the two classes. This emphasizes the importance of having a training session each time the user puts the headset on because the features that separate left and right motor imagery can change depending on the session and setup. With the one dataset we were able to collect, the PowerBin model was able to perform with approximately 60% accuracy, with the features on the right being the top 10 differentiating features. The alpha range appeared to be too noisy to be helpful in this case, but here we can see that the C2 electrode for delta range was among the top. By selecting the top 8 features for our model, we chose the number of features to be less than the number of trials to reduce the risk of overfitting. After analyzing the data, we built up the PowerBin model to classify our EEG data. We used PowerBin ratios that we saw earlier, along with average left side and right side electrodes for these PowerBin values, and the difference between these averages as parameters. We also calculated the Haworth parameters for the EEG data, one being mobility, which is the standard deviation of the power spectral density, and complexity being the similarity to a regular sine wave. Feature selection was done by finding the most separable features, and this was calculated based on the widest difference between the means of the two classes and subtracting the standard deviation for these two classes on those features. Additionally, we did model stacking in which we selected the best classification model that performed better with a leave one out methodology, and in the end, our model was able to average approximately 60% accuracy.
Hi, I'm Andrew, and I am one of the project members who worked on the calibration GUI and testing. In regards to neurofeedback, studies have shown that neurofeedback improves the usability of motor imagery BCIs. So, our neurofeedback is just a slider that shows the prediction of left versus right motor imagery in real time. In regards to what our interactive real-time app looks like, we have these 4 screenshots provided below. So in the screenshot to the leftmost, we basically have instructions for the calibration period. Users have the option to go directly to neurofeedback to use the app if no calibration desired. In the next image, we have the calibration procedure, which ensures the model is trained to tailor to the specific user. In the third image, we basically have a live data and predictions that can be seen in the data viewer after model is trained. And finally, we have the feedback procedure, which reports the model in action and can be used to train the user to perform the motor imagery task better.
Hi, my name is Ryan Abeloff, and I worked on model research as well as output commands in the output pipeline.
In order to determine which key would be pressed by the computer based on the operator, we use prediction probability. So once the operator thought they wanted to go left or right a certain amount, as determined by the model, a certain threshold would be hit and the key would be pressed in correlation based on left-right movement. In addition, there was a third action that is characterized by not really moving at all, so kind of staying in the middle between left and right, and that can correspond to any other key, whether it be up, down, enter, spacebar, whatever is really desired by the operator, whatever command they could use within Google Maps. So in terms of limitations, we have, I'd say, three main limitations. The first being that in terms of control, we only have three modes currently: left, right, and since we use the up arrow as our third kind of command that the operator can give, it only gives us forward. So something we can do is we can incorporate an idle state, allowing that user to stay stationary without having to move back and forth to see one address or one landmark. Another pretty big issue is that real-time decoding has a significant, about 5-second lag due to the necessity to fill that buffer with motor imagery and filtering edge effects. We can try using a shorter time trial to allow for faster decoding. That really depends on the way that the model responds, but I'm sure there is a solution that will keep that accuracy that we have while shortening that lag. The last issue, which is a very minor issue, is progression through the app. So actually getting to Google Maps where you can use the BCI commands requires click inputs. And that's an easy fix. We can just automate the sequence to allow the user even more autonomy. So once they've automatically gone through a training sequence, which we can set up as well, it will progress to Google Maps. So there will be no clicks involved, maybe just hitting a space bar or something to start the process. But after that, it'll be fully automated for the user for accessibility reasons.
So we have basically learned a lot when we worked on this project. But the most important things that we've learned from this project are to persevere through technical difficulties. And that was because we encountered issues where code was not working when team members pull from the GitHub repository. The second important thing that we learned is that real-time decoding is a big challenge in itself. And this was because we need to reduce lag and improve accuracy of our models. Third, every contribution matters because there are many parts to a BCI project to make everything work. And most importantly, be open-minded to all ideas. Thank you for listening into our project, and we'd like to give a special thanks to our faculty advisor, Vikash Gilja, the Dassault Lab, our ML mentors, Zoe and Colin, and our sponsors. And if you want to learn more about our club, you could visit our website, Facebook page, and or Discord channel through the following links provided in this slide. Thank you.